Let's see.
The intuition behind the second step is the following. Remind yourself, bit shifting a number to the left doubles it, and shifting it to the right halves it. But what would happen if we did something like this to an exponent? Doubling an exponent squares the number, and halving the exponent gives us the square root. But now also negating the exponent gives us 1 divided by square root of x. That's exactly what we need. So let's remind ourselves what our goal is here. We have our numbers stored into y, and our goal was to calculate.
Let's just look at what it does. I just want to see
that number.
So yeah, this is like the magic number, and this thing divided by 2. Okay.
Reminder is to an exponent. Exponents get divided by square root of x.
Just got the idea to do a little side project to make a keyboard shortcut to speed up or slow down the speed of a YouTube video.
That's exactly what we need. So let's remind ourselves what our goal is here. We have our numbers stored into y, and our goal was to calculate 1 divided by square root of y. As I've already said, calculating this directly is too hard and too expensive. But we've extracted the bits from y, and we've seen with the IEEE standard 754 that the bits of a number are in some sense its own logarithm. That means in I, we have stored log of y, up to some scaling and shifting. I claim that our problem becomes way easier if we work with logs. Instead of trying so hard to calculate 1 divided by square root of y, we instead calculate log of 1 divided by square root of y. We rewrite this to log of y to the power of minus a half, so we can take up the exponent. Calculating this is stupidly easy. You might think, oh no, we have a division in there. Didn't you say in the beginning that divisions are slow? Well, yes, but remember that we can do bit shifts now. Instead of dividing by 2, we just bit shift once to the right. This already explains why we do minus I bit shifted once to the right. But why is this number 0x5f37590f here again? Well, because our logarithm is actually scaled and shifted. So let's calculate and understand where it comes from. Let gamma be our solution. Then we know that log of gamma equals to log of y to the power minus a half, which equals to minus a half times log of y. Now we replace the logarithm with the bit representation. And then we just solve for the bits of gamma. I'll spare us the details, but this is the result. Magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting. Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from those bits. Well, actually, not the exact solution, just an approximation. This is why we need the third step.
What was the, where did the magic number come in?
To be the remnants of the error term mu.
So this magic number is, I don't know, I guess you're like collecting these terms right here. It's like 3 halves thing. Maybe this, maybe this. I thought this magic term was the, I forget how it was used, but it was like, this was like the mu term. I thought this was the mu term. Guess not.
Scaling factor and the shift, the approximation. Did pick up the approximation. And what Newton's
yeah, where do we come back with the mu term?
Does is that it takes an x value and tries to guess by how much it is off, ultimately equal to x. If you think about it, this approximation is actually correct for x equals 0 and x equals 1.
It took too long. between watching this video, I got out of the flow.
But we'll add an additional term, mu. This correction term can be chosen freely. Again, with...
I'm gonna rewatch this video.
But before we start with these 3 steps, let's first take a look at binary numbers. We said that in the first
should just be a refresher
line, we declare a 32-bit integer in a C programming language called a long. That means we're given 32 bits and we can represent the number with it. But I think you all know how to do that. This is 1, 2, 3, 4, and so on, up to around 2 billion. But in the next line, we declare 2 decimal numbers in C called a float. Again, we're given 32 bits and we have to represent a decimal number with it. How would you do that? If you and I were designing decimal numbers, this is probably one way we would do it. Just put a decimal point in the middle. In front of the decimal point, we count in the usual way. 1, 2, 3, 4, and so on. And after the decimal...
Let me get this, let me get a picture of the thing. Put this somewhere. Got this song stuck in my head, by the way. Get hyped. Just that step number. Found. Want that? You let it go. Listen.
Point there, no surprises either. Just remind yourself that this is binary. So instead of tenths, hundredths, and thousandths, we have halves, fourths, eighths, sixteenths, and any combination of them.
Got to go back and re-get the intuition for all this. Oh well, it's okay. Let's see this Wacom thing. It's always finicky. Yeah, see, there we go. Okay, this thing. Plugged it into another port and now it detects it. Let's see, all right, yeah. Okay. So just thinking about the, he said instead of like tenths, hundredths, thousandths, we have halves. So this is like tenths, hundredths, thousandths. We have halves, fourths, eighths. So this is like 1 over 10 to the 1, 1 over 10 to the 2, 1 over 10 to the 3. This is like 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3. And the ultimate goal is to have it so kind of with like infinite precision, you can sum up to 1. So if you kind of had, like 0.9999999, like whatever, that's basically like 1. And in binary, if you had like 0.111111, like that would also approximately be 1. It's like a tenth plus 100 plus 1,000th. It's like a half plus a fourth plus an eighth plus a, whatever. So
like a half and a fourth give you 3/4, also known as 0.75. But this idea is actually terrible. We've decimated the range of numbers we can represent.
Said decimated, like we're trying to like come up with a decimal and we've like decimated this number. It's kind of funny.
Or we could represent numbers to around 2 billion, now only to about 32,000.
No.
Luckily, people much smarter than us have found a better way to make use of those 32 bits. They took inspiration from scientific notation. The same way we can systematically represent numbers like 23,000 as 2.3 times 10 to the 4 and 0.0034 as 3.4 times 10 to the minus 3, we can also represent them in a
It's kind of interesting with scientific notation. You kind of, it's almost like a form of encoding where you just take like the information in the number, and like that's the only part that you explicitly kind of like encode, I guess. And you take like all the stuff that can be represented a lot more compactly, like these 3 zeros. It's kind of like a run length encoding thing where you just kind of say like 0 and there's like 3 following them. But this is kind of like, yeah, this is like 10 to the 3 basically. And this thing is like, I don't know, you got like 3, 4, and this thing is like something like 10 to the negative 2. Yeah, it's just interesting how this encoding kind of works.
4 as 3.4 times 10 to the minus 3. We can also represent them in a binary system, where here, for example, 11000 could, for example, be 1.1 times 2 to the 4.
It's kind of interesting to think of it like that. 1.1 times 2 to the 4. Yeah, I guess in kind of like a similar way. Because when you multiply by 2 to the n, you basically just like add n zeros. I guess more specifically, you like move the decimal place n spots to the right. This is to the right, yeah. And then this would be like to the left. To the left. Everybody taking the left.
The standard they came up with takes the name IEEE 754. IEEE standard 754 defines the following. We are, as usual, given 32 bits. The first bit is the sign bit. If it is 0, the number is positive. If it is 1.
So the whole, just recall, like, I guess like the whole point of this is we're like encoding decimal number. This is like a float. This is how like a float encodes decimal number.
Number is negative. But the numbers Quake 3 provides to the fast inverse square root are always positive. I mean, obviously they're positive. If we would have to calculate 1 divided by square root of -5, something definitely has gone wrong. So for the rest of this video, we ignore the sign bit, as it is always 0. Then, the next 8 bits define the exponent. That means 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. With 8 bits, we can represent numbers with...
Yeah, it's good to just kind of, maybe in my mind, just like solidify this in my mind. Like when I just see a float, just kind of basically think of this representation. It's kind of like 32 bits, and you got, yeah, you said like the exponent. It's like pretty simple. It's just like the sign bit, the exponent, and then there's going to be the third part.
0 and 255. But that's not exactly what we need. We also want negative exponents. This is why everything is actually shifted down by 127. So instead of 2 to the 4, we actually have 2 to the 4 minus 127. If we actually want the exponent to be 4, the bits need to be set to 131, because 131 minus 127 is 4.
Gotcha. So yeah, this exponent's like positive, negative range. Said negative 127 to 127.
The last 23 bits are the mantissa.
Mantistatus.
As usual in scientific notation, we want to denote one digit, followed by the comma, followed by the decimal places. But with 23 bits, we can represent numbers from 0 to, but not including, 2 to the 23. Again, that's not exactly what we need. For scientific notation, we need the mantissa to go from 1 to 10, or in binary scientific notation, to go from 1 to 2.
1 to 10. I think I did this before, but 1 to 10, I guess like in decimal notation, you could have like 9.4321 like this, times 10 to the 5th. It's like whatever number. I guess it's kind of like going back to the previous slide when we said, all right, what is scientific notation? It's kind of like taking all the numbers that are kind of non-zero and kind of like just writing them out. So all your digits are like digits, I guess like 0 to 9. So you kind of just like write all those out. And if you just think about like, and your number is always going to be in the form of like number followed by a decimal, followed by like some more numbers, and that's it. And so if you kind of like whatever, just think about all possible combinations of these numbers. This could basically be like a 1 up to a 9. This could be like a 0 up to a 9. This could be a 0 up to a 9. And so the highest possible number, I guess, would be like 9.99999 times 10 yen. And I guess like the lowest possible number would be like, it'd be like 1.0000, like 1.0, I guess. Numbers 1 to 9. No, basically 1 to 10, he was saying. Basically like 1 up to 10. Did he say 1 up to 10 or 0 up to 10?
That's not exactly what to, but not including, 2 to the 23. Again, that's not exactly what we need. For scientific notation, we need the mantissa to go from 1 to 10, or in binary scientific notation.
Yeah, 1 to 10. 1 to 10, 1 to 2.
To go from 1 to 2. So we could do something that we've already done before. Put a comma after the first bit. This automatically gives us numbers from 1 to 2. But this naive approach is wasteful. You see, the people that designed standard 754 realized that in binary something happens that happens in no other base. Look at the first digit.
Look at it. Look at it.
In scientific notation, the first digit is by definition always non-zero. But in binary, there is only one digit that is not 0. 1. And if we know that the first digit will always be a 1, there is no need to store it. Thus, we can save 1 bit by moving the comma 1 digit to the left and fixing an extra 1 in the number it represents. Now, our mantissa is between 1 and 2. Even though 23 bits gave us numbers between 0 and 2 to the 23, we scaled them down to get numbers between 0 and 1.
Yeah, so I think just when I'm thinking of floating point floats, it's kind of like the first pass, kind of like simplest thing to think of is just to kind of think of like a sign bit followed by the exponent, followed by the mantissa. What is that like in scientific notation? I guess you got the sign bit, you got the mantissa, just like 9.321. This is like the mantissa, and then times 10 to the sine. No, not sine. Exponent like this. So it's kind of like the sine times the mantissa times 10 to the exponent. That. Yeah. So this is kind of like the first pass. The sign bit basically just like stays the same. You said the exponent though. So there's all this, it's kind of like this trick layer where you do some tricks. And the exponent, you basically take it and then you subtract 127. It's kind of like a little trick, little shifting thing. And then the mantissa is like you treat it kind of with like, I don't know, if you think of like the mantissa as like M1, M2 to Mn, then we kind of treat the mantissa as like mantissa 1 dot M2, M3, Mn. So this is like the first trick. But then with binary and specific, there's like a further trick where you're like, all right, just treat it as like M1, just treat it as like 1 dot M1, M2, Mn. It's kind of like that's the whole. It's kind of like that's the whole thing. It's pretty cool. Think of it like that.
And we added an extra 1 to get numbers between 1 and 2. And this already is the main part of IEEE Standard 754, but just the so-called normalized numbers. The informed viewer knows that the standard also includes denormalized numbers, not a number, infinities, and 2 zeros. But we won't go into those, because in Quake 3 it just happens that these are never inputs into our algorithm. Otherwise, something definitely has gone wrong anyway. At no point should our game engine have to normalize a vector with infinite length. For this algorithm and for the rest of this video, it will be useful to think of the mantissa and the exponent as the binary numbers they are. If we are given two numbers, one being the mantissa and one being the exponent, 23 bits and 8 bits respectively, we can get the bit representation with 2 to the 23 times e plus m, if you think
Oh yeah, okay.
about it. Because multiplying e by 2 to the 23 just shifts e by 23 digits. So that's how one could write the bits, but we get the actual number behind the bits with this formula. This should seem familiar to you. Here we have the exponent with 127 subtracted from it, and here we have the mantissa with the extra 1 in front.
Okay, so yeah, this is like getting the number. So if you're just like given the mantissa, yeah, I guess this is, so you're given this wait, the mantissa over 2 to the 23. Why would you shift it over 23? Oh, this is like actually division. This isn't just like bit shifting. This is actually like moving the decimal place over. No, I don't understand this.
should seem by 20 with 2 to the 23 times e plus m, if you think about it. Because multiplying e by 2 to the 23 just shifts e by 23 digits. So that's how one could write the bits, but we get the actual number behind the bits with this formula.
Oh, okay. I guess, yeah, okay. I guess dividing it by 2 to the 23. So by itself right here, yeah, this number is just a huge positive number, but we actually want to view it like this, just kind of like put a decimal place in front of it. So it's basically like taking the, this is kind of how it is right now. And what we want to do is treat it as that decimal. So we kind of like move the decimal place over like 23 spots to get to like this point right here. And then we just add the 1 back. And so we get like 1 point this. So that makes sense. And then, yeah, we take the exponent and we shift it down 127. And then we do 2 to that power. And that's like the actual number. Yeah, that makes sense.
This should seem familiar to you. Here we have the exponent with 127 subtracted from it, and here we have the mantissa with the extra 1 in front. But now something completely different. For no obvious reason at all, let's take the logarithm of that expression. Since we're doing computer science here, we take the logarithm base 2. We simplify as much as we can, take out the exponent, but then we get stuck. But by as much as we can, take out the exponent, but then we get stuck. But not so the creators of Quake. Developer Gary Taroli knew a trick to get rid of the logarithm. You see, the trick is an approximation to log of 1 plus x.
Yeah, this is this
Small
thing.
values of x. Log of 1 plus x is approximately equal to x. If you think about it, this approximation is actually correct for x equals 0 and x equals 1. But we'll add an additional term, mu. This correction term can be chosen freely. Again, with mu equal to 0, this approximation is correct at 0 and 1. But it turns out that setting mu to this number gives the smallest error on average for numbers between 0 and 1. So going back to our formula, we apply our trick, as m divided by 2 to the 23 is indeed a value between 0 and 1. As
Yeah, for values of x between 0 and 1. Sure, yeah.
Divided by 2 to the 23 is indeed a value between 0 and 1. We rearrange a little bit more, and we finally see why we did all those calculations. M plus e times 2 to the 23 appears. That's our bit representation. So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants.
So like this expression is like, so we started off with like y is equal to basically this thing. Yeah. So like this is y, like this is like float of y right here. And so to get the log of y, like we just take the, basically it's just like y times 1 over 2 to the 23 plus mu minus 127. Divided by, yeah, this division's weird. This isn't exactly just shifting down by 23. This is like actually just kind of treating it as like a decimal thing. Yeah, this is to get the actual number. I'm a little bit confused between saying it's just shifted in scale, because this isn't just a shift. Oh, unless, wait. Well, it is 32 bits, so maybe he did mean maybe this is actually just shifting, because shifting away these 23 bits 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. So shifting 23 bits is basically just chopping this off. So maybe it is just shifting this down, and then you just get this thing. I mean, then like this expression would just be the exponent. So why wouldn't you just write this as like the exponent plus mu minus 127? The log of y is equal to, it's not equal, it's like approximately equal, because that's where this mu thing came in. We dropped the log. Yeah, 1 over is kind of like these kind of things both undo each other, and then I guess also that. So you're just left with like the exponent.
So in some sense, the bit representation of a number is its own logarithm. Armed with this knowledge, we can finally start with the 3 steps of the fast inverse square root.
Okay, evil bit hack. All right, let's see if we can get here.
The intuition behind the second step is the following. Remind yourself, bit shifting a number to the left doubles it. And shifting it to the right.
All right, I'm pretty hungry. I'm gonna grab some breakfast. That was cool. We kind of went through and got some more intuition, kind of big picture for stuff. Let's pick it up next time and hopefully hit the ground running. See ya. Peace.